For example, right here, if I'm standing on the planet and I consider myself to be inertial and I would draw myself as a world line that's straight, right? This theory would say, if it were a model of gravity, that in fact your world line is not a geodesic of space-time. You're drawing this naive T-R axis, and your line is along the T-axis, but the T-axis that you're drawing is actually non-geodesic. And your world line has a curvature relative to the actual geodesic, and that's just technically called geodesic curvature. So suddenly my timeline, the T-line of my naive axis system, has an actual curvature. If I drop an object right near where I'm standing, and it'll have a certain acceleration, there's a relative acceleration between us. That relative acceleration will exist in any theory. In the Newtonian regime, where it's, let's say, gm over r square, I certainly will expect that if I am now told I have a curved world line and I have an acceleration, my acceleration will be very much like this gm over r square. So the roles are reversed, and in this way of looking at it, you would say that, of course, anytime you go into a non-inertial frame, you're rotating and moving in strange ways, and you look at an object, you see it. If you think of yourself as stationary, you think it's rotating and accelerating and so on, so you're going to ascribe that motion to some kind of a force, and you're going to invent a force, right? In the same way, you would say, obviously, instead of inventing a force, just get into an inertial frame, right? So we would say the inertial frame is a free fall frame, and in that free fall frame, you see that these, everything works out. If you're standing on the planet from an true inertial frame, actually you see yourself as accelerating. And you don't feel any forces on you when you're in this free fall frame, and therefore you understand that you're inertial.